In this class, we will focus on what the Elastic Load Balancer service is and what it does. So, the main function of the Elastic Load Balancer, commonly known as ELB, is to help manage and control the flow of incoming requests destined to a group of destinations by evenly distributing these requests. These destinations could be a fleet of EC2 instances, Lambda functions, a range of IP addresses, or even containers. The targets defined within the ELB could be located in different availability zones for additional resiliency or all placed within a single availability zone. Now, these ELBs are managed by AWS and scale based on incoming traffic. This means you can focus on managing your application while AWS manages the load balancer for you. Let's look at this from a typical scenario. Suppose you have just created a new application that currently resides on a single EC2 instance within your environment and is being accessed by multiple users. At this stage, your architecture can be logically summarized as shown. If you are familiar with architectural design and best practices, you would realize that using a single instance approach is not ideal, although it would certainly work and provide a service to users. However, this infrastructure design brings some challenges. For example, the single instance where the application is located may fail, perhaps due to a hardware or software failure. And if that happens, the application will be down and unavailable to users. In addition, if you experience a sudden spike in traffic, the instance may not be able to handle the additional load based on its performance limitations. As a result, to harden the infrastructure and help correct these challenges, unpredictable traffic spikes and high availability, among others, you should introduce an Elastic Load Balancer and an additional instance to run the application in the design as shown here. As you can see in this design, the Elastic Load Balancer, or ELB, will act as a point to receive incoming traffic from users and evenly distribute the traffic among a larger number of instances. By default, the ELB has high availability, as I said before, since it is a managed service provided by AWS. And so, they ensure its resiliency so we don't have to. Although it may appear that ELB is a single point of failure, the ELB is in fact composed of multiple instances managed by AWS. So, as you can see in this scenario, we have 3 instances running our application. Therefore, if an error occurs on any of these 3 instances, the ELB will automatically detect the error based on the defined metrics and divert traffic to the 2 remaining healthy instances. In addition, if you experience an increase in traffic, the additional instances running the application will help with the additional load, and this is because the ELB is managed by AWS and is, by definition, elastic. This means that it will automatically scale to meet the incoming traffic as the incoming traffic scales up and down. If you are a system administrator or DevOps engineer running your own load balancer by yourself, you have to worry about scaling the load balancer and enforcing high availability. With an ELB, you can create your load balancer and enable dynamic scaling with just a few clicks. Now, depending on your traffic distribution requirements, there are 4 ELBs available in AWS to choose from. First, the Application Load Balancer, or ALB. It provides a set of flexible features for web applications running HTTP or HTTPS protocols. The ALB offers advanced features such as routing, TLS termination, and visibility, allowing precise control over how traffic is distributed, even to different ports on the same EC2 instance. For example, you can direct traffic to different ports on the same EC2 instance, allowing you to have multiple services running on a single machine and still maintain precise control over how traffic is distributed. Then, there is the Network Load Balancer, or NLB. This NLB provides exceptional high performance for your application while managing very low latencies. It operates at the connection level, directing traffic to destinations within your VPC. In addition, it has the capacity to handle millions of requests per second, making it a robust and efficient solution for managing your application traffic. Then there is the Gateway Load Balancer. This is a service that helps you deploy, scale, and manage third-party virtual network applications such as firewalls, intrusion prevention and detection systems, analytics, visibility, among others. For example, imagine you have a large-scale network with multiple subnets and you are using network security appliances such as firewalls or intrusion prevention systems. In a high-traffic scenario, efficiently managing these appliances can be a challenge. So, this is where the Gateway Load Balancer comes into play. You can use it to distribute traffic evenly to all your security appliances. This not only ensures that all appliances are used effectively, but also facilitates scalability, as you can add or remove appliances as needed without disrupting traffic flow. Finally, the classic load balancer. This tool automatically distributes incoming traffic among multiple EC2 instances to ensure that no instance is overloaded. For example, if you have a website with variable traffic, the CLB can help distribute user requests evenly among all your EC2 instances, ensuring that your website runs efficiently at all times. Now, before going into the details of these load balancers and their practical demonstrations, let's talk a little bit about the components, since, without knowing about them, you will not be able to implement them correctly. So, for each load balancer, regardless of the type used, you must configure at least one listening agent. The listener agent defines how incoming connections are routed to the target groups based on the ports and protocols set as conditions. The settings of the listener agent itself differ slightly depending on the ELB you have selected. Then there are the target groups. A target group is simply a group of resources to which you want your ELB to route requests. For example, a fleet of EC2 instances. You can configure the ELB with several different target groups, each associated with a different listener configuration and associated rules. This allows you to route traffic to different resources based on the type of request. We also have the rules. Rules are associated with each listener agent that has been configured within your ELB and help define how an incoming request is routed to which destination group. As you can see, your ELB can contain one or more listening agents. Each listener agent can contain one or more rules, and each rule can contain more than one condition, with all rule conditions equaling a single action. An example rule might look like this. In this case, the rule we see in the image is one that the listening agent would be listening for. So, when a request arrives that matches this source IP address and the HTTP request method is PUT, the listening agent triggers the rule and forwards the request to group 1. Thus, the listening agents allow the ELB to respond dynamically to incoming traffic, ensuring that requests are handled as efficiently as possible according to the defined rules. Then we have the health checks. The ELB associates a health check that is performed with the resources defined within the target group. These status checks allow the ELB to contact each destination using a specific protocol to receive a response. If no response is received within a set of thresholds, the ELB will mark the destination as incorrect and stop sending traffic to that destination. Then we have the schema, where we are going to find the internet-facing options and the internal ELB option. With the internet-facing option, as the name implies, the ELB nodes that are defined as internet-facing are accessible through the internet and therefore have a public DNS name that can be resolved with a public IP address. This allows the ELB to service incoming requests from the internet before distributing and routing traffic to its target group, which in this case could be a fleet of web servers receiving HTTP or HTTPS requests. When your internet-facing ELB communicates with your target group, it will only use the internal IP address, which means that your target group does not need public IP addresses. Now, an internal ELB only has an internal IP address. This means that it can only service requests that originate from within its own VPC. For example, you could have an internal load balancer sitting between the web servers on the public subnet and the application servers on the private subnet. We also have the ELB nodes. Then, during the process of creating your ELBs, You must define in which availability zone you want your ELB to operate. For each availability zone selected, an ELB node will be placed within that availability zone. As a result, you must ensure that you have an ELB node associated with the availability zones to which you want to route traffic. Without the availability zone associated, the ELB will not be able to route traffic to any destinations within that availability zone, even if they are defined within the destination group. This is because the ELB uses the nodes to distribute traffic to the destination groups. Finally, we have cross-zone load balancer. Depending on the ELB option you select, you may have the option to enable and implement cross-zone load balancer within your environment. Let's assume you have 2 availability zones enabled for your ELB and each associated load balancer receives the same amount of traffic. One availability zone has 6 destinations and the other has 4 as shown here. So, when the cross-zone load balancer is disabled, each ELB and its associated availability zone would distribute its traffic to the destinations within that availability zone only. As we can see in the image, this results in an uneven distribution of traffic for each destination across availability zones. Now, with the cross-zone load balancer enabled, regardless of the number of destinations in an associated availability zone, the ELBs would distribute all incoming traffic evenly among all destinations, ensuring that each destination in the availability zones would have an even distribution. So, with all this information about ELBs, let's look at how to implement them.